So we're going to study matrices. Our next topic is matrices. And we know what a matrix is already because we've been playing with it. And you might have seen it before coming into this class. But really, this becomes the heart of this class. This is when you think about linear algebra, you think about matrices. And so everything we do is based on dealing with matrices. And matrices are all over the place. And one first application that we've already discussed is the systems of linear equations, where we take the coefficients and we make a matrix out of them, and then we do some row echelon form business. But there's actually more to matrices, and we can create matrices from pictures. Do you guys know that? You can create matrices from pictures. So a picture is just a bunch of pixels, and each pixel has a certain color or intensity or something like that, and so that certain color or intensity will reflect one number for that one pixel in a matrix. And so I've been trying to fiddle around with this in MATLAB, and I don't have anything prepared yet, but hopefully next week I could show you how a picture becomes a matrix, and then how, if we mess around with that matrix, you can mess around with that picture as well. Wow, that sounds like a good worksheet. Sounds like a good worksheet activity.
It's a way to create filters.
Yeah, a way to create filters. You can filter. Yeah, there's a lot of neat things you can do. So that's another application of matrices. Matrices can sometimes be used to transform things, linear transformation. So if you have a picture and you pass it through a matrix, you can rotate it and you can skew it, and you can do all kinds of neat things. So let's talk about matrices, introduce matrices today, some basic operations, and then dive into some deeper operations later on. So a matrix is a rectangular array of numbers, and in each of those numbers would be called an entry or an element of the matrix. The size, it's important to be able to identify the size of the matrix. And the matrix, since it's a two-dimensional array, we can think about it as a row and a column. It's important when we say the size of the matrix that we're saying the number of rows first and then the number of columns. So when I say that we have a 3 by 5 matrix, your matrix will have 3 columns, or 3 rows, sorry. Just trying to make a big deal out of it, and then now I'm slipping up. It has 3 rows and then 5 columns. So it's important to be able to identify the size and identify it correctly by saying the correct thing. And then we'll see why this is important, especially for matrix multiplication, where the size of the matrix has to agree with itself. We've been dealing with vectors, and sometimes we put something up and call it a row vector or a column vector. So when we're talking about vectors, we can also refer to them as matrices, and they're a special type of matrix. So a 1 by m matrix has 1 row and m columns. So 1 by 3 matrix will just be essentially a row vector. And then 3 by 1 matrix will have 3 columns, or 3 rows, and 1 column. So this is our basic convention for determining the size of a matrix. Okay? In some applications, they might start these things a little bit differently. I know in computer science, you start with 0. People tend to like to index it at 0. But here, we're going to start with the first element in the first slot as a 1 by 1. And we'll talk about labeling these as well later on. All right, let's see. So it might be important to access the elements or the entries in a matrix. And so for that, we're going to, and you've seen a little bit of this in the free mat, if you've gone through the last worksheet. So we use this double subscript business. And refer to the first subscript, I is the row, and then the J is the column. So when we have, what's the size of this matrix? So 3 by 4. Well, we want to identify this particular element in this matrix, depending on what we call this matrix. Let's call this matrix A. So, and this is convention. Sometimes they use the whether it's capital or a little lowercase, doesn't matter. So this one would be on the second row and in the third column. So by pulling that out, extracting that, you're going to get your matrix element in the second row and third column. And it's done the same way in MATLAB or free mat, which kind of makes it nice. So the numbers agree with us. If you do it in different computer language like Python or something, then you have to. It's not the 2 and 3 that you put in. It's actually a 1 and 2 because you're starting with 0. Makes it a little bit more confusing. But in this case, it's easier for us. Yeah?
So you're writing this as 23?
Well, you see 23, but you say 2, 3.
Or what if you have 3 digits?
Well, if you do that, then like if you're in a 20th column or 20th row and 31st column, so you probably write A 20 31 and try to write it, just a little bit separately. Oh, or no, this is what they do. They put a comma. Yeah, I think that's what they do. Yeah, that's what they do. They end up putting commas on those things. Yeah, so that's usually a lot of the things that we do by hand. We can get away with doing something like this because if we're going to do it by hand, it can't be too big. But when it starts getting really big, then I think they start using comma. So here's another comment that they had. Sometimes a matrix is represented by a group of columns or row vectors. And so we have to look at them as M vectors taken as columns. So these are column vectors. And you put the column vectors right next to each other, they make up a matrix. And then likewise, these are row vectors. And if you put a bunch of row vectors together, you make up a matrix. Okay. And when we're dealing with matrices, sometimes we're interested in identifying, singling out one column or singling out one row. And when we do that, this is how we're going to identify it, as a column vector or row vector. Diagonals also play an important part of the matrix. As you can guess, or just probably visualize, if you have a matrix, you just go down the diagonal, and when I say diagonal, I mean the diagonal that goes down this way. So that would be the diagonal matrix. And so those diagonal entries will be 1, 1, 2, 2, 3, 3, etc. And then that will identify your diagonal entries. Now, if you have the same number of columns and rows, then that is called a square matrix, obviously, because it's square. It's not a rectangular matrix. A square matrix whose non-diagonal entries are 0 is called a diagonal matrix. So that means if you have a matrix that looks like this, where everything else except for the diagonal is 0, then this is called a diagonal matrix. And it turns out that these diagonal matrices are easy to deal with, and so they become special for us. And in fact, one of the things that we're going to do is we're going to take a matrix, a random matrix, we're going to take it apart so that we can see its diagonal. Or we can look at a matrix as a product of some diagonal and something else. And so we'll get to those things later on in the semester. So it turns out that if you have an identity matrix is a diagonal matrix with 1s in the diagonals. And so that is going to be important for us. So the identity matrix would be something that looks like this. And it's a special kind of matrix. So it's usually denoted by a capital I, and then if we know that this is, first of all, an identity matrix has to be a square matrix. And so we can denote this by just the number of rows, which is equal to the number of columns. So if I say I3, then I get my identity matrix 3 by 3. Kind of, not quite unit vector, but use the word unit here. In math, or in math, in arithmetic, you know, the number 1 is our unit value, unit real number. So when we learn multiplication, we'll see that, you know, 1 times anything is itself, right, or whatever that anything is. And we learned that as a special property for real numbers, that there's that special number 1 where that gets multiplied, and then you're going to get the original value. So the unit, the identity matrix is the same thing. It's like a unit matrix where when we learn multiplication, we'll see that a matrix times the identity vector, or the identity matrix, is going to equal to the original matrix when we learn multiplication. Okay, and then there's a 0 matrix. It would just be all zeros. So for this 0 vector, or the number 0, we write 0, but I tried to make a big deal that when we have a 0 vector, I insisted on putting an arrow on top of the 0. So this is a number 0, and then an arrow on top would make it a 0 vector. So similarly, just to avoid confusion, if we have a 0 matrix, we could just put square brackets around it. Now the size of this matrix is important too, so it'd be nice if we put in a subscript as to what the size is. But in general, if we just put 0 with the square brackets around it, we know that it's going to be a 0 matrix. And if the size of that matrix is obvious, then we don't need to put a subscript. Oh, it's also doesn't necessarily have to be a square matrix, so you may, in terms of putting the size, you may need to put the number of rows and the number of columns. So that's just notation. And so all this stuff kind of coincides with the stuff that we're doing with the commands that are available in MATLAB. Should we take a look at MATLAB, FreeMat? Let's see if there's anything else I need to talk about here. Matrix. I'll take a look at that in a minute. Let's take a look at FreeMat or MATLAB and take a look at some of the commands for matrices. So we can create a matrix in several ways. I talked about stacking up vectors or stacking up, stacking up vectors. Let's make up a couple of vectors. V1 equals 1, 2, 3. V2 equals 4, 5, 6. So we can stack them up as if we treat this as row vectors, as in one of our examples, we can set up a matrix with these things as the rows. So I'll take V1 as my first row, and then to get to the next row I need to use a semicolon. So I'll take V2 as my second row. And now I have a matrix. This matrix is a 2 by 3 matrix. If I want to access the second column and the first row, what's the first row and second column? What number is that? So that's the 2 up here, right? So if I want to access the first row and the second column, all I have to do is type in A and then in parentheses, and then I would get that. And so the other neat thing about this is that I can actually change that value. So A1, 2, let's make that a 0, and then now that 2 that used to be a 2 up here now became a 0 because I've went in there and physically changed it. So MATLAB also does the identity matrix. You know, the identity matrix, I say it's like I3 or something. Well, in MATLAB, I is I, your I. So if I want a 3 by 3 identity matrix, I would type I, E-Y-E, and then I would get that. So what's cool about this is that you can quickly, without having to type in, you know, the rows and the columns, I can quickly do a 20 by 20 identity matrix, and then I would have this thing with zeros everywhere except for the diagonal. Okay. So what else did we talk about? Yeah. What do you mean? I suppose. Let's see.
Is there any Boolean values?
Yeah, there's Boolean values. I think there's true and false. Yeah, true is 1, false
Yeah,
is
you
0.
can do that. With expectation.
Okay, well, let's see. Let's do I1 or I3 equals identity matrix if I3 equals I3. Do I do print? Can I print here? Print F. Anybody know MATLAB?
Well, you can create a Boolean variable and assign that to the Boolean.
No. I'll just say x equals
Well,
2. So I3. I don't think so. So I3 equals 4. And let's see if we could do that if statement again. Yeah, so the first time I ran it, I3 was actually equal to the identity matrix. And it gave me, I ran whatever was inside of the if statement. Here I changed I3 to equal to just the scalar 4. And then I ran that if statement again, and this time it didn't give me anything. So I think it's a Boolean. You can do that in an if statement.
you can use printf.
Printf. Yeah. So I was going to do that, but it's over. We can move on. So there's a lot of ways to create matrices. You can create matrices. Oh, we created a matrix from those 2 row vectors. Well, we can also create a matrix from those 2 column vectors. So let's say B is equal to V1 was a row 1, 2, 3, but I'm going to make it a column 1, 2, 3 by putting this quotation. Did you guys do that yet? Have you guys done the apostrophe? That is called a transpose, and we're going to learn about that, the transpose idea later. So this is going to be the first column, and then V2 will be the second column. And so now instead of having a 2 by 3 matrix, here I have a 3 by 2 matrix. And then I can also create a matrix of zeros by putting 0 or zeros. Let's try 0 first. And then I can have a 3 by 3 matrix if I just put one number 3 in. Oops, that's zeros. Or I can be more specific. If I just want a row vector, I can just put the 2 dimensions in there, the row, the number of rows, and the number of columns. Okay, so there's a lot of neat things that you could do. You can build matrix, and MATLAB, the name mat comes from matrix, not math. And so this is actually built to process matrices. All right, let's move on to some basic operations of matrices. it turns out that you can add matrices and you can do scalar multiplication of matrices. You can subtract matrices. And in algebra or even arithmetic, they talk about the zero identity property and the additive and the multiplicative identity property. So we haven't done any matrix multiplication yet, so we'll talk about the multiplicative property later. But for now, let's talk about the additive identity and additive inverse. So matrix addition, it's important that the two matrices that you're adding have to be the same size. And as you would guess when you do this matrix multiplication or matrix addition, you would just add component by component. For the scalar multiplication, when you multiply a matrix by a scalar, you would multiply each and every one of those elements by that scalar. And the difference is like addition with scalar multiplication when you scalar multiply by -1. And the additive zero identity property says that 0 plus the zero matrix plus anything is going to be itself. And the additive inverse property says that if you add the negative inverse, then you should get the zero matrix. Okay, so these are basic properties for addition that we've all learned, except for that scalar multiplication, which is a little bit different. But we saw that in vectors, and so that shouldn't be that big of a deal. Notice that the scalar multiplication is different from a row operation. We talked about row operations with matrices where we multiply only one row. Scalar multiplication multiplies not just one row, but all the elements in the matrix. Okay. So you guys don't need to see examples of this, do you? Well, if you do, I'll do it in MATLAB. Let's build a couple of matrices. I think we have A and B, but they're not the right size. So my A matrix is a 2 by 3 and my B is a 3 by 2. So if you try adding them, you'll see that you're going to get an error because it's not the same size. So maybe we'll add on to matrix A. Let's add on another row. What row are we going to add on? 1, 1, 1, 1, 2, 3. Yeah, let's put 1, 2, 3. So this has to be a row matrix that I need to add on. And then for B, let's add on another column. What column should we add on? 6, 7, 8, 9. 7, 8, 9. It has to be a column matrix, so I'm going to make it a column matrix. So I have A and B here now. Let's add A and B now, because now that they're the same size, it should be comparable. You should be able to add them. So if you add them, 1 plus 1 is 2, 0 plus 4 is 4, 3 plus 7 is 10, etc. So that's the addition part. Scalar multiplication, we could take a matrix and multiply it by a scalar. And what that's going to do is going to take your matrix A and multiply each one by whatever scalar you multiply it by, in this case by 5. Subtraction will work the same way. And then the other business. So multiplication is a little bit different though. So that's, let's see what A times B is equal to. What did I get here when I multiply A times B? Let me try something else. These are two types of multiplication in MATLAB. There's A times B, and there's A, and then here's a dot times B. What do you think about those two operations? Can you tell me what's going on here? Can anyone identify either of them? The second one looks like it just multiply each element. So A and B are here. Where's A and B? A is a little bit off the screen here. So this is A. If you multiply 1 times 1, 0 times 4, 3 times 7, you're going to get 1, 0, 21. So in MATLAB, there's a nice matrix multiplication. If you put a dot before you do the multiplication, multiply, then it's telling MATLAB to take each element and multiply it. But clearly that's not what's happening here. Something else is going on over here, right? So this multiplication over here is the true matrix multiplication that we're going to be using in our class. This matrix multiplication where you multiply element by element is not what we want to learn. MATLAB has that capability for doing certain things, but it's not what we're interested in. So let's talk about matrix multiplication now and how they got those values. So matrix multiplication is this long, complicated looking formula, and I do expect you to be able to do this by hand and not rely on a calculator or MATLAB or something like that. Because your calculator has matrix options too, and you can do these matrix multiplications really easily. But I'm going to want you to be able to do this by hand. So this looks complicated. But let's see if we can demystify this. So let's use the same values or same matrices that we were using in MATLAB here. A and B. As our example. So if you have matrix A and the matrix B, this it looks really complicated. What you want to do is this, I don't know if you can see it clearly, but this is really a dot product of some sort. This tells you if you're looking at the ijth element of your result, of your answer, then the way you would find that is you would take the ith row for A and the jth column for B, and then essentially do a dot product, and then that's going to give you your ij for the result. All right, so that whole thing is confusing, but let me just show you how to do it where it might be easier to understand. Let's say this is C11. This is our result that we want for C11. So how do we get C11 here? So C11 is going to be equal to taking the first I is equal to 1 and j is equal to 1. Taking the first row of A, and j is also equal to 1, taking the first column of B. And what we essentially want to do is we want to multiply 1 times 1 plus 0 times 2 plus 3 times 3. And so that's going to equal a 10, right? So our first element in our C11 matrix, or C matrix, is 10. So now let's go to C12, the first row and the second column, C12. So we're going to take 1, the first row of A, and this time we're going to take the second column of B. And then we'll do the dot product of that. So 1 times 4 plus 0 times 5 plus 3 times 6. 4 and 18, 22. Now let's try another one. Let's try this one, right? No, let's try C32. So to find the third row and second column of C, the third row, so the rows are always going to be associated with the first matrix, and then the columns is associated with the second matrix. So here it's 1 times 4 plus 2 times 5 plus 3 times 6. This one is 30, 32, 32. All right. So it might actually be better if these two are kind of situated next to each other. 1, 0, 3, 4, 5, 6, 1, 2, 3, 1, 4, 7, 2, 5, 8, 3, 6, 9. And if you're looking at it like this, when you do your multiplication, so my first element here is going to be the first row and first column. So again, that's a 10. To get to my second number, it's the first row and the second column, which we got to be 22. To get the third number, it's the first row and the third column. So this is 7 plus 0 plus 27. 7 plus 27, 24. Is that right? 34? 24. 34. You see what I'm doing? Going a little bit quicker now. Now I want, if I want this spot over here, I'm interested in my second row now. Second row and first column. So that's 4, 10, then 18. What is it? 26? What? 4 plus 10, 14, plus 18, 32. Okay? And then the next is to get my middle element, it's the middle row and middle column. So that's 16 plus 25, that's 36, I think. Plus 36 is 72. And then 4 times 7 is 28. 28 plus 40, 68. 68 plus 54, 1. What is it? What? Instead of 72? Was that wrong? I thought it was 36 plus 36. Oh, what's 16 plus 25? 31? Oh. All right. So what should it be? Back up over here. 77. I'm not very good with math. So 28, 40, that's 68, 124. All right, we go to the last row. Man, this is painful. 1, 4 is 5. 9 is 14. All right, next. Sadly, I've relied too much on technology to help me find these answers, and so 4, 10, 18. Didn't we do that one already? 32. And then the last one, 7, 16, and 27. 50? Oh, man. Does that look right? Boy, I'm glad I don't have to take the test. Anything else we need to fix? All right. So that's how you do matrix multiplication. An important aspect in this matrix multiplication is that we didn't really see this aspect in this example because we multiplied a 3 by 3 and a 3 by 3. But according to this matrix multiplication statement over here, we have an n by r and an m by r. Uh-oh. Let's try that again. We have an m by n matrix that we're multiplying an n by r matrix. And the result is an m by r. So what's all that mean? That means that the matrix sizes that we're multiplying doesn't have to be exactly the same. In this case it was, that we multiplied 3 by 3 and a 3 by 3. But the only thing that has to coincide in terms of multiplying the two matrices is we have to have the same number of columns for the first matrix as we do the number of rows for the second matrix. Okay? Same number of rows, same number of columns. So let's multiply. Let's do an example where we're multiplying matrices that aren't the same sizes. So let's do another example. Let's take a look at an A matrix that has let's go with a 3 by 2. 1, 2, 3 by 2. 1, 2, 3, 4, 5, 6. And let's multiply. Let's get another matrix that has 3 by 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. Uh-oh, these numbers are getting too big. And let's take another matrix, and let's say this is a 1 by 3. 1 by 3. 1, 2, 3. So if we identify these matrices by their sizes, 3 by 2, 3 by 5, and a 1 by 3, right? Those correct? Number of rows, number of columns. So the question is, can we multiply A times B? So A times B, A is a 3 by 2, and B is a 3 by 5. And so what you want when you're multiplying these two things is you want the same number of columns for the first matrix as a number of rows. If you were to try to multiply this, what you would do is you would take the first row here, and you're going to try to dot it with the first column here. Now clearly that's not going to work because these two are the same, or these two are different sizes. So does not work. No, yeah, can't multiply. Because they have different sizes. I can, however, multiply maybe a 1 by 3 with a 3 by 2. So C is a 1 by 3, and A is a 3 by 2. So if I multiply these two matrices, I see that I can, first of all, I can multiply these two matrices. But you can also see something by analyzing the dimensions. You can also see or expect what your final resulting matrix will be. And it turns out that your final resulting matrix will be a 1 by 2 matrix. All right, so if we're saying that we can actually multiply this, let's see if we can multiply this. This is a 1, 2, 3. Multiply it by 1, 2, 3, 4, 5, 6. Well, if I know this is going to be 1 by 2, I should expect something like this. So the first row, I only have one row here to deal with, but the row in the first column, 2 times 3 is 6, that's 7. 7 plus 15, 22. So that takes care of my first element, and then my first row and second column, multiplication dot product thing, I have 2 plus 8, that's 10, plus 18, that's 28. So I end up with a 1 by 2 matrix. Okay, so you can see that with matrix analysis. So this kind of gives us the idea that you know, in all this time that we've been talking about math, even with vectors, we could switch the order of the vectors to do the dot product. In other words, the dot product is commutative. That's like saying 1 plus 3 is the same thing as 3, or times. It's like saying 2 times 3 is the same thing as 3 times 2, right? So all those numbers that we've been dealing with have been commutative. This now is not commutative. And so that's an important aspect of matrix multiplication, is that this is one of those first things that we're learning that's not commutative. Yes?
So you can do C times A, but you cannot do A times C, right?
In this case, you can't even do A times C. It's not work. So you can what? Not that you decide the order, but whenever you're multiplying, the first thing you should check is to make sure that the first matrix that you have, the number of columns in the first matrix you have, matches the number of rows on the second matrix. So not only that, but so this is saying that something like this doesn't work is one thing, but saying that it's not commutative is something else. Because like with square matrices, we can multiply them, but if we switch the order, we might get a different answer. And so we'll see that in a few minutes. Yeah? Zero vector. If you transpose a zero vector, if it's a row vector, it becomes a column vector, then that would be it. Oh, yeah, if you're trying to get some sort of multiplication out of a problem, then you may need to transpose something. All right. So before we do this extracting elements business, let's continue talking about the matrix multiplication not being commutative. So we have A times B equaling to one matrix, but if we multiply B times A, it turns out that we're going to get two different matrices that are not equal to each other. So I think this is important to note. So we'll copy A times B again, or A and B, and then we'll copy the results of A times B and B times A. So this is our example to just note matrix multiplication is not commutative. Even if they're the right size, like for square matrices, like in this case, so you have 3 by 3, so if you multiply them in any order, they can work. But if you multiply A times B and multiply B times A, you'll see that it's not going to be equal to each other. There's some special cases where they are. That means the original matrices have some special properties. But in general, matrix multiplication is not commutative. You can't get the same result by switching the order of multiplication. Okay? Any questions? All right. So Let's take a look at a couple more properties for matrices. So in MATLAB, we can find an element in the matrix by just identifying the row or row and column. But it turns out that you could do something else with a special operation or a special type of vector or a special type of matrix. So let's take a look at how to extract an element by multiplying things. So let's suppose you have a matrix, an m by n matrix, and then you have two vectors. The Ej vector is a 1 by m unit vector with a one by m, so one row. So what this is that I'm looking at zeros everywhere else except for the ith entry in that vector. And then we could take a look at the Ej as the same sort of vector, where it's a column vector with zeros everywhere else except for the jth component. So instead of that neat little command in MATLAB where we could just say A parentheses Ij, here we could actually multiply by a unit vector to extract that particular element, or in this case it's extracting the particular vector. And you can combine these two operations to get the element itself. Does that make sense? I don't know if that makes sense. Let's see how to make sense out of that. I think I could do this without MATLAB. So let's say A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. That's going to be one of my favorite matrices for a while. So if I want to extract the second row and the third column, and I'm looking at this number 6, right? This first one says I could take what is this? Row vector 0, 1, 0, and then multiply it with A. And then I can get the ith row for that. So I can, by doing this by doing this matrix multiplication, I should get the second row, right? So let's see how it actually works. So I only have one. Oh, by the way, I think I want you to get used to writing this down so you know what to expect for your answer. So 1 by 3 and a 3 by 3 will give us a 1 by 3 matrix, right? So a result should be a 1 by 3 matrix. And if I take a look at my first row, my only row, and my first column, 0, 4, 7 to 0. So this is just 4. And then I move to the next column, 0, 5, 0, 5, and then 0, 6, 0, so that's 6. So this is getting my ith row. So now here, if I take my matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9, and if I multiply that by a column vector, this time I want my j to be 3, 0, 0, 1. So it's a unit vector with zeros everywhere except for the third spot. So I'm going from a 3 by 3 to a 3 by 1. So my result should be a 3 by 1 matrix. That looks like it's going to be a column vector. So the first row and my only column, 0, 0, 3. I move to my second row, 4, 4, 6, so 0, 0, 6. And then I move to my third row, 0, 0, 9. So that's what the theorem is saying. You can extract that. But what I was saying is that you could go even further, and there should be a C to this. C, EI times A times EJ is going to give you the ijth element of A. So if I were to take 0, 1, 0, excuse me, times the matrix A times the vector 0, 0, 1. If I do the first multiplication, I know that that's 4, 5, 6 because I already did that. And then I do my second multiplication, I get 0, 0, and 6. And that's my 2, 3 element in my matrix. So you can extract it by doing matrix multiplication. And there's a lot more matrix multiplication that we're going to learn. We're going to take that back to the idea of the basic row operations. There's a lot of elementary matrix operations that we'll need to learn. All right. See you guys next week.